Question 2 then. Let's start off with a straight fact that you need to know. The approximate size of a hydrogen atom, it's that one, 10 to the minus 10 metres. That's just something for you to remember. Figure 1 is a diagram of 3 atoms. Explain why these atoms are isotopes. Right, as soon as you see the word isotope, straight away in your brain you should be saying to yourself, same number of protons, different number of neutrons. That is the key thing with isotopes at GCSE and A-level. It's just a definition they love for you to trot out again and again and again. And you can see that with this, because it's clear that these are isotopes because they've got the same number of protons, 1 proton in each, but they've got a different number of neutrons, 0, 1 and 2. So it's a 2 marker, same number of protons, different number of neutrons. You can see from the mark scheme. You could say it in slightly different ways. You could say it's got the same atomic number, in other words, same number of protons. You could say it's the same element, in other words, same number of protons. Remember, the number of protons determines what kind of element you have. All iron atoms have 26 protons, all gold atoms have 79, etc, etc. Other one you could have said, different number of neutrons or different mass numbers. It means pretty much the same thing. Okay. Moving ourselves on, some isotopes are unstable. They emit beta minus particles when they decay. Explain how the nucleus changes when a beta minus particle is emitted. Right, well, a beta minus particle is an electron. Let's clear that up straight away. Again, this is really just facts for you to recall rather than anything you've got to work out here. Inside the nucleus of something that's about to decay by beta minus, essentially you've got too many neutrons, not enough protons. Sometimes it works out that way. So we've got too many neutrons, not enough protons, so here are a few protons but not enough of them. It's not a nice ratio, the whole thing is unstable. When it decays by beta minus radiation, we know a little electron is given off. But they're asking what's happening in the nucleus. In the nucleus, what happens is a neutron, let's say this little fella here, is going to turn into a proton. So now we've got 1 more proton and 1 less neutron. Notice the number of particles in the centre hasn't changed. The number of particles in the nucleus is exactly the same because we've got 1 less neutron but we've got 1 more proton. And this way the ratio of protons to neutrons becomes a little bit better and the thing gets closer to stability or sometimes reaches stability. So in the mark scheme they're looking for you to say that the number of neutrons has gone down by 1, there's 1 mark. Number of protons has gone up by 1. There's 1 mark. I mean, if you say that a neutron has turned into a proton, you've basically covered both of those things in one neat little sentence, haven't you? Wonderful. Other unstable isotopes emit alpha particles. What are alpha particles? They're pretty much helium nuclei, because an alpha particle is 2 protons and 2 neutrons. And a helium nucleus is exactly the same. Of course, a helium atom will also have a couple of electrons in there. There's one, there's another, there's a helium atom for you there. But if you just look at the nucleus, 2 protons and 2 neutrons, that is the same as what alpha radiation is. Clearly it's been a long day. Part E, we're looking at a picture of Rutherford's experiment. They're asking you how the results of the experiment support the nuclear model of the atom. Now, key thing here, they're not asking you to say how this looks like an atom. They're not asking you to say that this represents the nucleus and this represents electrons going around it, as some people got confused with. What they're asking for is how this experiment showed that there was a nucleus inside the atom. So they're asking you to trot out your well-worn by now explanation of what Rutherford's experiment actually showed. So here are the key ideas from Rutherford's experiment. It can go up to a 6 marker, this sort of thing, so make sure you've got your details. Rutherford fired a load of alpha particles at some thin gold foil. He expected all of them to blast straight through, and for him to detect a load of alphas here and none of them around here. Because the current model of the atom at the time was the plum pudding model.